Good morning, student. Today we will continue the chapter magnetic effect of current. In the previous class, we have discussed that when current flows through a conductor, then magnetic field is produced around it. And we have discussed about the direction of magnetic field, and to know about the magnetic field, we have discussed about the magnetic field lines concept, and we have discussed the patterns of magnetic field lines. So all about the things we have discussed, the direction of magnetic field due to straight current carrying conductor. Today we will discuss about the magnitude of magnetic field due to current carrying straight conductor. Magnitude of magnetic field, suppose this is a straight conductor carrying current I, and this is the perpendicular distance A from the conductor to the point P where we have to find the magnetic field. Suppose you have to find the magnetic field at point P. So students, in class 12, you have to know how to find the magnetic field by using Biot-Savart law. In class 10 syllabus it is not there, but on what factors the magnetic field depends is in your syllabus. So to know that, I have written the formula. Biot-Savart law, you can write, those students who want to know, Biot-Savart law tells about the magnitude of magnetic field at distance r due to current element IDL, and that is mu naught by 4 pi IDL sin theta by r square. So this is the current carrying element, this is IDL at distance r, this is the magnetic field dB. So these things is not in your syllabus, so don't concentrate on that. Using this Biot-Savart law, we have derived the formula for magnetic field due to straight current carrying conductor at distance A. So this is the formula. So if you keep this formula in your mind, then you can tell on what factors the magnitude of magnetic field depends. So you can see the magnitude of magnetic field is directly proportional to the current. Current is in the numerator, mu naught by 4 pi is constant, 2 is constant. So it is directly proportional to the magnitude of current. So magnitude of magnetic field due to straight current carrying conductor depends on magnitude of current. What does it means? That if you increase the current, then magnetic field will also increase. Means if you increase the current by 2 times, magnetic field at particular point will also become 2 times. So if you go on increasing the current, the magnetic field at this point, a particular point P, will also go on increasing. By the factor, you are increasing the current. If you decrease the current half, then magnetic field also decrease here to half. Next point is, you can see BA, this perpendicular distance is A and it is in denominator. What does it mean? If you increase A, making current constant, current must be constant, and suppose you are increasing A, example, suppose this I current is flowing, this is not changing, and you have increased the distance, suppose this is 2A. So what will the magnetic field here? So by this formula you can see it is inversely proportional to A. If you will increase this denominator, then B will, if you will increase denominator, B will decrease. If you will decrease the denominator, B will increase. It is inversely proportional. So if you are go on increasing the distance, suppose you are going to a distance of 2A, in comparison to current is constant, remember current is not changing. So if the distance increases to 2A, so when it became 2A, then magnetic field became half. When it will become 4A, magnetic field will become 1 by 4. Similarly, when you will decrease the distance, suppose you come to A by 2, you come here, A by 2 distance. So what will be the magnetic field? The magnetic field will increase by 2 times. So that is meaning of inversely proportional. And the last point, you can see one term is there, This is permeability, and this depends on the medium surrounding the current carrying conductor. If it is not air, another medium. If it is air, then it is okay, mu naught. If it is not air, another medium, then it will also change. So you can write the third is nature of the medium. Nature of medium. So these are the factors which decides the magnitude of magnetic field at any point due to straight current carrying conductor. Similarly, we can discuss for circular current carrying conductor. Now, by using Biot-Savart law in class 12, we are deriving the formula what is the magnetic field due to circular current carrying conductor. Suppose this conductor is not straight and it is circular. The picture here, it may be seems to you that it is not the circular, but I am drawing the circular picture only. Suppose this has the radius A. So you are not concerned with the derivation. I am writing directly the formula what by Biot-Savart law. What formula we are getting at center O? The magnetic field formula is mu naught by 4 pi 2 pi I by A. Clear? The formula is nearly same. Only here pi comes into existence. You can write the same formula as mu naught by 2 I by A. So you can see, students, nearly the formula is same, and so the factors affecting the magnetic field at the center of the circular coil will be also same. You can see magnetic field is directly proportional to the current. So first, magnetic field due to circular coil at the center, current carrying circular coil, current at the center. So what are the factors? The magnitude of magnetic field due to current carrying circular coil at the center. So what are the factors? First, the magnitude of current. Magnitude of current. You can see B is proportional to I. Means if you will increase the current, the magnitude of magnetic field at this point also increases. If you will decrease, the same, vice versa. Next, this radius. If you increase the radius of the circular coil by 2 times, if you will increase by 2 times, magnetic field became half. If you will decrease the radius by half, magnetic field became 2 times, inversely proportional. So second factor which is affecting the magnitude of magnetic field at the center of the circular coil carrying current is radius of the coil. Radius of the coil. How it depends? Inversely proportional to the radius. If you will increase the radius of the coil, then magnitude of magnetic field will decrease. Here. And of course the third point is the medium between the circular coil. So third is nature of the medium. So this point is very important. Generally question is asked from this point. If the radius of the circular coil carrying current becomes half, what will be the change in the magnitude of magnetic field at the center? So you have to write it became 2 times. So that's about the magnitude of magnetic field due to current carrying conductor. Next is Next is about the conductor is carrying current. All the things we have discussed about the direction, we have discussed about the magnitude, we have discussed. Now we will discuss certain things which is, you can say, application of magnetic effect of current. That is about the solenoid, about the electromagnet. What is solenoid, what is electromagnet, and where it is used, and how we are using this, and the rules like Fleming left hand, right hand, which is used in electric motor, electric generator, that we have to discuss in this chapter. So we will discuss today only about the solenoid. Solenoid, you can see, suppose a current carrying coil you are folding like this. Suppose current is entering here and current is leaving here. So when you are folding the current carrying coil in this way, such that the radius of each circular coil is same, means radius of each circular coil which you are making is same, and the number of turns, this is 1 turn, this is 2 turn, 3 turn, 4 turn, number of turns is very large as compared to the radius. Suppose this is radius A. So if the number of turns which you are making, you are go on, suppose you take one wood, or suppose this is the pen, and I am coiling the conductor, suppose wire, around this. So I will, and then I will remove this, I will get a helical coil, that is known as helical coil, means cylindrical coil. And when you pass the current through that cylindrical coil, that is known as solenoid. So you can write the definition that solenoid is the helical coil or cylindrical coil in which the number of turns is very large as compared to the radius. Number of turns is very large as compared to the radius. Suppose you are making only 4 number of turns. So that will be not solenoid. The number of turns must be very large, maybe 50, maybe 100, and as compared to the radius, suppose radius is millimeter, 1 millimeter. So the number of turns must be very large. Then only it will be a solenoid. Now when it is seen that when current is passed through a solenoid, then it starts to behave like a magnet. It develops 2 poles, one north, one south. So if it is developing 2 poles, how it is how this is seen that it develop 2 poles? Generally, you bring one magnet, and if you bring one magnet near the current carrying solenoid, you will see one pole. Suppose north pole you are bringing one at this pole. Suppose it is repelling, so this will be north pole. When you will bring this north pole here, suppose it is attracting, so this will be south pole. So it is seen by experiment that current carrying circular coil, cylindrical coil behaves like a magnet. So when it behaves like a magnet, then the magnetic field lines will be also same as we have drawn for a magnet. It will start from north pole and end at south pole outside the magnet, and the direction you have to practice in your home. Inside the magnet it will start from south and end at north. Start from south and at north. This already we have discussed for the magnet. So the magnetic field lines that we have drawn for magnet, you have to draw for solenoid. When question is asked, draw magnetic field lines for a current carrying solenoid, then you have to draw like this. Second thing which you have to know, that when current is flowing through a magnet, then what is the way to know which will be the north pole, which will be the south pole? There is some rule which will tell you about the north pole and south pole. In your book it is given clock face rule. Clock face rule means, suppose you face the one side of the solenoid. Suppose the solenoid is carrying current like this. So if you are seeing from my side, I am seeing this, and it will appear that current is flowing in clockwise direction to me. But when you are observing, you will see that current is flowing in anti-clockwise direction. So if you are observing from that side you will see that it is anti-clockwise. So that side, your side, will be north pole. And when in my side, if any observer is here, he will feel clockwise direction. That side will be south pole. So very simple clock face rule: face your face toward one side of the current carrying circular coil. If it seems to you that current is flowing anti-clockwise, that is north pole, and if you will feel that current is flowing clockwise, that is south pole. For example, suppose current is flowing like this. So I am observing from my side that current is flowing clockwise, but you are observing that current is flowing anti-clockwise. Means your side will be north pole and my side is south pole. So clock face rule is used to determine the polarity of two poles of a current carrying solenoid. Current carrying circular coil, that is solenoid. So what is clock face rule? If we face to one side of a solenoid and current seems to flowing in anti-clockwise direction, that will be north pole, and the other side from which if we face our face and the current seems to flowing clockwise, that will be south pole. This is the one rule which is given in your book. Second rule is very simple: Ampere's right hand rule. Means this is the right hand and you fold your fingers in the direction of current. When you fold the finger in the direction of current, they will indicate the north pole. This will indicate the north pole. This is in class 12, just for understanding, because question is asked, that diagram will be given to you and it will be asked, tell the north and south pole. So very simple, in examination you can apply this rule, that in the direction of flow of current, suppose current is flowing like this, current is flowing like this. Clear? So fold the finger in the direction of current. This will be the north pole. That is known as Ampere's right hand rule. So this is the rule. And third is the magnitude. The magnitude of magnetic field inside the solenoid. Inside the solenoid is the formula mu naught Ni. You have to not concern with the formula. It is in class 12. But in class 10, the things is given that state the factors on which magnitude of magnetic field inside the solenoid depends. So outside the solenoid, the magnitude of magnetic field is very small and it can be neglected as compared to the magnetic field inside it. You can see the magnetic field lines is straight and parallel. So this will be uniform magnetic field, uniform magnetic field. And what about the magnitude? Magnitude of magnetic field inside the solenoid depends on, you can write in your copy, magnitude of magnetic field inside the solenoid depends on, first, magnitude of current, and second is number of turns per unit length, and third is nature of the medium. You can see, student, that magnetic field is directly proportional to the current. If you will increase the current, if you will suppose you connect this solenoid with 12 volt battery. In spite of 6 volt, you are connected 12 volt. So more current will pass. So this will produce more magnetic field inside the solenoid. Second, number of turns per unit length. Means in unit length, maybe 1 centimeter, maybe 1 millimeter, what length you are taking. In unit length, how many turns? Suppose in unit length 4 turns are there. So magnitude of magnetic field is less. If you increase in unit length, suppose 10 turns are there. So magnitude of magnetic field will increase. So it depends on the winding which you are making. Suppose you are coiling the coil closer to each other. So number of turns per unit length will increase. So magnitude of magnetic field will also increase. And third, the nature of the medium. Generally the air is inside the solenoid. If you take some another medium also, if you increase this factor by taking another medium, then magnetic field also increases. We will see that when we will insert a soft iron, this will change and the magnitude of magnetic field will increase. Because why this happens? Because we are increasing this factor. We will see in the next class how it will increase. So magnitude of magnetic field inside a solenoid depends on 3 factors: number of turns per unit length, magnitude of current, nature of the medium. So students, you can see the 2 terms are common, that is magnitude of current and nature of the medium in all the expression. So you can understand this, that 2 things are common, and in all the question you have to write these 2 things at least. That magnitude of magnetic field directly proportional to magnitude of current, and it depends on nature of the medium. So we will stop here and we will join again with the same topic in the next class. So thank you to all, and if you have any problem, you can contact me directly and ask the question. Thank you.